because I didn't film anything yesterday. All right, here we go. Easy, easy today. But a lot of, just because it's easy, make sure we start gathering or understanding the concept of this. Golly, I'm so glad you guys are back. I missed y'all. Seems like forever since I've seen you. It's been a week, I guess. Beautiful. Let me make sure I turn this thing on. Show it. That's what I need. Slideshow. Ta-da. Probability. So let's focus on this. All right, chapter 5 and chapter 6 are units 4 in AP Classroom. So when I assign AP Classroom, there might be something on chapter 6. It'll kind of make sense on that, right? So when that happens, that's when somebody lets me know. So whenever somebody gets there first, they're going to let me know, hey, this question's from chapter 6. And that way I know to either try to remove it or whatever I can try to do to that. Okay? So randomness, probability, and simulation. Hi. Button. On. Yeah. You want to do it now? Okay. Chance is all around us. Chance is all around us. We play rock, paper, scissors to see who's going to get the last slice of pizza. Or we're going to give it to the bigger person so that they don't hurt us. A coin is tossed to determine who's going to get the football at the start of a game. Incidentally, there's a pretty big game this next weekend. Or Friday. Many adults regularly play the lottery, hoping to win a jackpot with few, grab that chair, that desk. Many adults, not this guy, hoping to win the big jackpot with few lucky numbers. So, few lucky numbers. One time, I don't play the lottery, but when it gets really, really big, some people play it. And I don't know why they play it then and not when it's small, because even when it's small, it's still pretty big. But you still have the same chance of winning. Well, there's a lot more people playing it. Doesn't matter. You still have the same chance of winning because you're trying to match numbers. And it doesn't matter if somebody else, the only thing is if somebody else matches the numbers, you split the money. Still a lot of money. Anyway. Others head to casinos, not me, or racetracks, or hoping that some type of combination in luck and skill will pay off. Young people and old play games of chance, cards, dice, spinners. We could actually have traits that your children inherit. Hair color, eye color, blood type, handedness, dimples. Rather, you can roll your tongues. That's all determined by chance. Because you either can or can't do it, or some can, some can't. You either win or lose, yada, yada, yada. Mathematics of chance is called probability. Anytime we're dealing with chance, it's called probability. You will probably win. You will probably lose. Haha. No, not really. Probability. Okay, mathematics of chance. All right, so let's do this. Kind of watch and learn. This, again, is common sense, but it's something that we got to, please work. I changed it yesterday because it didn't work. Beautiful. All right. Our heads are wrapped around a short-run behavior. I think everybody knows that if I toss a coin, it's a 50-50 chance of getting heads or tails, provided it's a fair coin. So, toss a coin, could get a head, could get a tail. I'm going to count the percentage of those that get heads. Okay with that? Go. One time, toss. There's the true probability, 50%. You may or may not can see that line at 50%. Toss it. 100% of my flips have been heads. 100% have been heads. Toss it again. 200, or still, I said 200%. 100% are still heads because I'm 2 for 2. Good enough? If it's a fair coin, at some point I'm going to get a tail, right? So let's just say I get 10 heads in a row. That does not mean the next flip has a better chance of getting tails. But our heads are kind of somewhat determined that, right? We kind of think, you know what, at some point we got to start getting some tails to even this thing out. But you don't. It's another 50-50 chance. Okay? Many years ago, at this little town or this desert out in Nevada, I think it is. It's a desert. It's got real big buildings, really, really, really big buildings. They have this game. It's got a I don't know, a wheel, or it kind of goes around in a circle, and then they take this little bally looking thing or something, they put it in there, and it goes around too. And one of them goes one way, and one of them goes the other way, and at some point that little ball jumps in there, and you try to predict that number, or color, or third, or there's a lot of things you can do. Apparently, I don't know any of this stuff. That's just what I heard. Well, the what do they call it? I think they actually take money out of their wallet and try to predict this. So I think they call it betting. It started going down on this thing because people weren't playing it that much. Say again? So Vegas. Yeah, that's the name of that little town over there. Yeah, in the desert. And so the betting was going down. I'm sorry, betting. Yeah. Betting was going down on this game because there were all these other fun games to play. And then they put this thing called a tree. I don't know if it's called a tree or not. I'm really making that up. But what it did is it kept track of like the last 20 or 30 rolls. And when they put that up, the betting went up like 270%. That's kind of made up, but it went up a whole lot. Because this darn tree thing came up there and people started saying, you know what, that thing hit 23 times in the last 20 times. I'm going to go 20. It's short run behavior. That's short run behavior. 20 still has the same chance of getting hit, even though it's hit 3 times. In fact, I guess our short run behavior starts saying, you know what, it won't hit 20. Y'all kind of follow all that stuff? We got short run behavior. When I toss it again, I finally get a tail. So this thing's starting to slowly come down and get to that 50%. Oh, I got another head. I'm headed back up. Now I'm back down. Keep going, keep going, keep going. Yay. Very, very, very variable. It's going way up, going way down. Let's change that. $100 times. It actually went down below 50%. Now we're still going below 50%. Now we're going above 50%. It's all over the place. But what we start noticing about that thing, it's less jumpy. It's becoming more level, right? And it's because my denominator is starting to get pretty big. Did it go? My denominator is starting to get big. And as my denominator gets bigger and bigger and bigger and bigger, that numerator is going to get closer and closer to that 50%. And if that denominator is at 1 million, it won't matter if I get 10 heads in a row. It's still not going to change that 50%. Right? It might be 0.499999999, and 10 of them still make it 4.9999999. Good? Yay? Kind of understand that? We have to understand the long run behavior, not necessarily the short run behavior. Okay? Always keep that in mind. Here, that being said, boom, boom. Come on. There's it fluctuated right at the beginning. Here's 10 tosses. I jump it out to 500 tosses. Notice again, it's still way up here to the, but then it's starting to level out. Good? This is called the law of large numbers. And the law of large numbers is just that. As we observe more and more and more and more trials, as we observe more and more trials, the proportion of times a specific outcome occurs approaches that true probability. The proportion of times that a specific outcome occurs approaches a true probability. We're going to do this more and more and more and more. Eventually, we're going to approach that 50%, provided it's a fair coin, right? If we don't approach that 50%, then we're going to have to think it's not a fair coin. The law of large numbers. We have to understand the law of large numbers in order to start to understand probability, okay? Most of us understand it, but again, our minds want to try to play the short run. If I get 10 heads in a row, I'm more likely to get a tail. No, you're not. It's still 50%. It's still 50%. In the long run, you're more than likely to get more tails than heads. But again, that's the long run. Okay, beautiful. boom, click. Oh, flipping the coin, boom, boom, boom. Oh, yeah. Unfortunately, our intuition about chance behavior tries to tell us randomness should be all predictable in the short run. It's not. Some people use the phrase law of averages to refer to the misguided belief that the result of chance have to even out in the short run. Again, kind of keep that in perspective. All right, simulation. Let's talk for just a little bit because this does a better job than my notes do. Simulation, simulating, right? If something has a 50-50 chance of happening, we can simulate that a lot of ways. Flipping a coin is a way you can simulate that. You can assign the head to success and the tail to failure, or vice versa. It doesn't really matter. I could just grab 2 cards out of a deck of cards, grab 2 of them, mix them up, flip one of them over. If it's a 7, or it's 7, let's just say I know what they are, 7 and 8. If it's a 7, that's a success. If it's an 8, that's a failure. So we got to mix them up every time and just flip it over, right? I can use my calculator. I can tell them the random digit, a 1 or a 2. I can use the random digit table, ignoring the 3, 4, 5, 6, 7, 8, 9, 0, just using the 1 and the 2, deciding on if it's positive, negative, good, bad. Yay? Kind of all that stuff. That's what simulation is going to do. They're going to simulate an event happening. For instance, if there's a 1 in 6 chance, I might take a die and roll a die. If there's a 1 in 50 chance, I might take a die. Is there a 50-sided die? I don't know. I don't care. I'm going to say take a 50-sided die and roll a die. And whatever number comes up tells me what I'm going to get. Y'all okay with all that simulation stuff? Was somebody knocking at my door? Ooh, they're knocking at my door. All right, got it made? That was a much better day to go today than yesterday. Knuckleheads went yesterday. They were gone all class period. Okay, so let's talk about that. Simulation. The imitation of chance behavior. The imitation of chance behavior. Oh, you got kicked out. Oh, I see what happened there. Snooze, you lose. The imitation of chance behavior. We're going to imitate some kind of chance behavior. We're going to imitate it. And it's going to be based on some model, whatever model you guys choose, or whatever model will work that reflects that situation. It reflects that situation. So again, I mentioned several times, there's 28 of you cats in here. There might be 28 different models. As long as that model accurately reflects that situation, then that's what you can use. Okay? Most of the time, I'm going to use my calculator with a random digit table. Or random integer. Because I can tell it exactly what I want. Okay? So that's what simulation is. All right, here we go. Don't do this, don't do this, don't do this. I'll come this. Pepsi ran a promotion many years ago. And their promotion was if you go buy a Pepsi, a 20-ounce Pepsi, and you open up the cap and you look at it and the cap says you're a winner, or it said, please try again. It was very nice. It didn't say you're a loser. And if you won, you could go up there to the counter and turn that Pepsi cap in and grab another Pepsi. Or you could do it next week or whatever you want to do. You didn't have to do it right then. Okay? Good enough. So some of the caps said, please try again, while others said, you're a winner. Pepsi advertised a promotion with the slogan, 1 in 6 wins a prize. So that was their promotion. 1 in 6 is going to win. Okay, so now that's common sense. I think most of you guys are, I know you guys are freaking intelligent. So does that mean if I go buy 6 Pepsis, am I guaranteed to win one of those? No. Could I win one of those? Sure. Could I win more than one? Sure. Okay with all that? So that's what their claim is. Their claim is 1 in 6. Now, if I go buying 6 and I don't win one, do I think that their claim's wrong? No. If I go buy 200 of them and I don't win one, do I think their claim's wrong? Probably starting to, right? Starting to. So what they're going to do is simulate this. Simulate this. So here's what happened. A young statistician in the AP Stats class wonders if this claim is true. So what this cat did is told their classmates, go out, I want you to go get a Pepsi, because we don't want to go buy 30 of them. Each student bought one. So 30 students bought one of these Pepsis. And they came back and said, did you win or did you not win? Good, everybody okay, right? 2 of those 30 students got a winner. 2 out of those 30 got a winner. Well, again, I think we're fairly smart. I know we're smart. I don't have to say I think we're fairly smart. If there's 30 and it's supposed to be 1 in 6, I should have how many winners? Should have 5. Should have 5. 1 in 6 is x out of 30? 5. Because 5 out of 30 reduces to 1 out of 6. Now, would I be surprised if I got 6? Probably not. Would I be surprised if I got 4? Probably not. Would I be surprised if I got 5? No, not at all, because that's what I should get. They only got 2. We want to start thinking, I don't know if that's that's kind of starting to be that iffy area, right? That's kind of starting to be that iffy area. So here's what they did. How many words do you expect out of 30? We already said that. We should get 5. Is that guaranteed? It's not guaranteed. We already discussed that. Does this result give convincing evidence that the company's claim 1 and 6 is inaccurate? Well, I'm not going to really know until I do some simulations. So here's how I'm going to do this. Exit. I'm going to get my little calculator, and I'm going to clear all this stuff out. And I'm going to go to math, because yesterday I kept going to stat. I'm going to go to math, and I'm going to go over to probability. Okay? And I'm going to go down to random integer. And I'm going to go 1 and 6. And I'm going to assign some number as a winner, and the other 5 numbers are losers. Typically 1 is my winner. But if you don't like 1 and you want to do 3 as a winner, fair enough with all that? And so then I'm going to paste it, and I'm going to draw, and that's my first Pepsi, and I lost. There's my second Pepsi, I lost. There's my third Pepsi, I won. Pretty cool, yay? How many times did they do this? 30. I don't want to do this 30 times. So I'm going to cheat a little bit, and I'm going to hit math, and I'm going to go over here to probability, and I'm going to go down, and I'm going to go to random integer, and I'm going to do 30 of these guys. Whoops, get up here. 30. Paste it. Now I'm going to store that into L1, because if I do 30 down here, I just don't want to see a whole bunch of numbers. I'm going to store that in L1. How many times are you going to have to do this on your calculator? Never. But just this is what I'm doing. Okay? So there, uh-oh, it didn't go. Oh, that didn't do store. Well, dadgummit. Store. There it is. L1. So there's all those stupid numbers. There's a winner down there. Okay with that? So now if I go to stat edit, I'll see all these numbers. And that doesn't help me a whole lot. Here's, watch what I'm going to do now. I'm going to sort it ascending. L1. Enter. Now then, stat edit. 1, 2, 3. I only won 3 out of those 30. Okay with what I did? Good enough? Hit me. Nope. Nope. That's what I say. We're not going to spend time doing this because it doesn't test anything knowledge-wise. I'm just showing you what we should do. This is the simulation. Will you now have to write one down? Yeah, possible. Possible. As we go. Say again? Write down I'll give you a question here in a second. I'll give you one. Okay, if I wanted to do this again, I could go back and not sort it. I want to do this again. Do random integer, store that in L1. So now that's a second group. Okay with that? And then I want to sort it ascending. Uh-oh. Sort it ascending. Let's see how many I won this time. Stat edit. 1, 2, 3. I still only won 3. Holy cow. This 2's not looking like it's too rare. Fair enough with what I'm doing? Okay. What they're going to do is do that a bunch of times. 50 times, 60 times. And they're going to do a dot plot of that. And then we can see how many times 2 showed up. And if 2 never showed up, I'm going to think that that's rare because it happened when I did it. Fair enough with what I'm saying, okay? So again, we did this. We actually did this, and we got 2 winners. The calculator says we should never get 2 winners. Something's wrong, right? We know we should get 5 winners. We know we should get 5 winners. 4, 3, well, it happened twice. 2, I don't know. We got to do this a whole bunch of times, and we're not going to do it a bunch of times. They're going to do it a bunch of times and tell you the results. That's what happens with the rest of my slides. Beautiful. Where are they at? Here we go. Boom. Uh-oh, why are you not big? We will perform simulations to help answer that question, and that's what we just did. So forget that one. Oh, boom, 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 boom. Let's find out. Okay. Boom, and let's roll a die. Oh, they wanted to roll a die. That would take a whole lot longer than getting 30 of those, right? If I roll a die 30 times, I'd see how many I got winners. Okay. Psh, psh. Next problem. Beautiful. An attempt to increase sales. A breakfast cereal company decides to offer a NASCAR promotion. NASCAR. Cars. Anybody NASCAR fan? Anybody? 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 Yeah? Rally's better. Okay. It's all right. Each person has their own opinion. It can be incorrect. Each box of cereal will contain a collectible card featuring one of the following NASCAR drivers: Joey Logano, Kevin Harvick, Chase Elliott, Danica Patrick, that's Danica, she's cute, or Jenny Johnson. 5 drivers. What? She's kind of cute. They put those cards in the box. I just got the box until I got Danica. I quit. I'm just kidding. This is actually a true thing too. It's just a while ago because none of these drivers drive anymore. The company claims that the 5 cards are equally likely. So what does that mean? There's not one that's like less likely than the other one. McDonald's is doing their Monopoly money right now. They're not equally likely. Like there's one out there that there's only going to be one. That's the one I got to get. Okay. Beautiful. A NASCAR fan decides to keep buying boxes of cereal until she has all 5 drivers' cards. She's surprised when it took her 23 boxes to get all 5. That's a lot of cereal. Good enough for that? Here's what their question. Does this outcome provide convincing evidence that the 5 cards are not equally likely? So, to answer this question, we want to perform a simulation to estimate the probability it will take 23 or more boxes to get a full set of 5 NASCAR. And so what they will say is design a simulation that will simulate this story, this problem, however you want to do that, okay? So you could say, I'm going to take a 5-sided die. I don't know if there's a 5-sided die or not, but they don't care if you make up one. And I'm going to roll it until what? All 5 numbers show up. All 5 numbers represent each driver. And I'm going to count how many rolls it takes to get all 5. Good enough of that? That's a simulation that will simulate that. And that would be a type of question that they might ask you. I'm not going to ask you that question because there's 28 of you cats and you might have 28 different answers and they all be right and I'm not grading it. I'll be honest with you. How else could I do that? I'm going to take my little calculator and I'm going to do this right here and I'm going to quit this thing. Get out of this. Slow down. Quit. Clear, math, probability, get over there, number 5, 1 through 6, 5, 1, paste it. I don't remember. Kevin Harvick. 3. Now we're at 2 boxes. 3 boxes. 4 boxes. 5 boxes. 6 boxes. 7 boxes. 8 boxes. 9 boxes. Holy cow. 10. Is that the last one I needed? I still need a 5. What am I at? 8, 9? I'm at 10? 11, 12, 13, good gracious, 14, this has never taken this long. 15, 16, 17, I did put 5, right? 18, 19, 20. How many boxes did it take her? I don't know. I'll be honest with you, that's the most it's ever taken me to get all 5. I could do that again and see how long it takes me to get 5. I don't want to do that again, especially in this class, because you guys are unlucky. Sorry. 1, 2, 3, 4, 5, 6, 7. That's the way it's supposed to work. But I can't change outcomes. All okay with all that stuff? Beautiful, 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 beautiful. Man. Well, go back up here. I'm all over the place today. Psh. Psh. Describe how to use a random number generator to perform a trial of this simulation. There's the type of question you would see. Okay with that? Again, I'm not asking you that question because I ain't grading it. Let 1 equal Joey, 2 equal Kevin, 3 equal Chase, 4 equal Danica, 5 equal Jimmy. Generate a random digit from 1 through 5 to simulate buying 1 box of cereal, looking at which card is inside. Keep generating random digits until all 5 labels from the 1 through 5 appear. Record that number. Beautiful way of saying all that. Okay? Again, I'm not going to ask you that. Homework's not going to ask you that. They did used to do that. I haven't seen that question in several years. Here's a dot plot of 50 trials. How long did it take me? 20 what? 20? That would be my dot. That would be my dot because it took 20 trials to get all 5 drivers. It looks like it took, I don't know if that's 21 or 22 or 20. I think it's probably 22. It took 22 twice. It never took 23. It took 5, which is what it should take if they're equally likely. 1, 2, 3, 4, 5 times. I got it in just 5 boxes. 6 boxes took twice. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Half the time it took 10 or less. Half the time it took 10 or less. Talk to me.
On the thing that you were just on, it says that this outcome provides convincing evidence that all cards are not equally likely. Do you need to know how to answer that?
We're getting ready to.
Okay.
That's what's coming up next. Beautiful. Everybody okay? Can you answer that? Do you think you can answer that?
I don't think I used the right wording.
You don't think? What did you use? You mind sharing? Oh, you think it's a yes or a no? Let me ask, do y'all think it provides convincing evidence that it should take 23 or more? Does it provide convincing evidence that the 5 boxes are equally likely to show up? Say again?
On this or just her?
This or just her. So it took 23 for her, right? She thinks they're not equally likely to show up. This takes a little while to understand. I get it. I get it. This is the hard part of trying to understand this. She thinks it takes 23 or more. How many times did it take 23 or more? Never, right? Explain what the dot at 20, let's hit this. I'll get to the question. It's the dot at 20. The one instance it took 20 times to get all 5 drivers. It took 20 boxes to get all 5 drivers. It happened in this classroom. It took 20, right? I've done this now 3 times or 4 times, and it never took 20. The 7 yesterday was the highest I had. One trial where it took 20 boxes to get all 5 drivers. Y'all okay? But good. So each dot represents it took that many boxes or that many. It was one trial. It took that many boxes to get all 5 drivers. Here's their question. Use the results of this simulation to estimate the probability it will take 23 or more boxes. What are the chances it's going to take 23 or more boxes? How many dots do I have? 50? How many took 23 or more? 0? Maybe 2? If you wanted to say 2. 2 out of 50 is still a pretty small chance of that happening. They said 0 out of 50. So because there's 0% chance of getting 23 or boxes or more, how many times did it take her? 23. And there's a 0% chance of that happening, and it happened. Something's wrong. Fair enough? I mean, if that number was, if it only took her 15 boxes, I don't think I can dispute that. It happened 15 several times. It happened 15 or more several times. Say again? Correct. Correct. And if we did 1,000 times, there's no way 15 would show up. Okay with that? Or if it did, it would be very, very small chances. Good? Okay. So does this outcome provide convincing evidence that the 5 cards are not equally likely? It does. It does. Does it provide convincing evidence that they are equally likely? No, it does not. Okay? So it's so unlikely it's going to take 23 or more boxes to get a full set. This provides convincing evidence that the 5 NASCAR drivers are not equally likely to appear on the cereal boxes. Fair enough? Chloe, did I get you? Okay, let it soak in. Everybody else okay? Anybody? Anybody? If it was, where's that threshold we talked about in this class several times? What percent do we start thinking it is likely? 5%. I know that's still a low chances, but at 5% when we start saying, you know what, that could happen. It's not very likely, but it could. Hit me. Okay. It took her 23 boxes. You're good with that? Everybody else okay? I know, this is hard for some people to get. So these questions are phenomenal. Some people just doesn't quite get there. So we simulated that this was going to happen if it was equally likely. If it was equally likely, the 1 has an equal chance, the 2 has an equal chance, the 3 has an equal chance, the 4 has an equal chance, and 5 has an equal chance on my calculator, right? And I did it one time on mine. There's my 1 dot. I did it the second time. I had a dot at 7. So I did this. I didn't do this. They did this 50 times. If it took 23 and it was likely to happen, I should have a whole bunch of dots around this area, right? It took her 23. If we expect 23 to happen, it should have happened several times. It never happened. So if it never happened, I don't think it's equally likely. I don't think. Mm-hmm.
But I don't understand what 23 has to do with the equally likeliness. If anything, I would think like them not being more than 23 makes it more likely than if they were all more than 23.
It makes it more likely that they're not equally likely to show up. It makes it likely that they're not equally likely to show up. Not that they are. If they are equally likely to show up, I should be getting some of these numbers down here.
Okay, so that's, I get that.
Okay.
Like, wait, can we go forward a couple to the thing we were just on?
It is so unlikely, in fact, it was 0% chance that it took 23 or more boxes. This provides convincing evidence that the 5 NASCAR drivers are not equally likely to show up.
They're saying because they got 20, it took them 23 times. They're saying this card probably has a bunch more of them in every cereal box than all the other 4.
Or 1 card's missing. 1 card's not equally likely to show up. My card was what, 5? My 5 didn't show up until the 20th. It didn't take, I mean, it took them 23 before they got the 5. Yep. Yes. If it was a 5 or higher, we would still say, I question it, but I'm going to say, I can't say no. Yep.
Would it be likely for it to be 22 or more boxes based on the?
Not on this dot, because that's only 2 out of 50, which is still under 5%.
Would have to be 5%.
We like it to be 5%. Okay. Go ahead. He said, what if it only took 22? Okay. Well, that happened twice. Well, twice out of those 50 is 4%. That's still under 5%. I'm still going to say they're not equally likely to show up. If it took her 20, now I'm iffy. because now I'm at about the 5%. I'm at the 6%. I can still say, I'm questioning it, but I think they're equally likely to show up.
I guess I just like was I don't necessarily don't understand how the 23 connects to the likeliness because I would think it would be like around 5.
Correct. Correct. No, I agree with you. That's what it should take. And it did. It took 5 several times. It never took 4, right? Because it's impossible to happen at 4. Got to have 5 boxes. Got to have 5 boxes. And that happened several times. These happened several times. I think they're equally likely to show up all throughout here, starting right around in here where we start thinking, I don't think so. I don't think so. Okay. Does this mean the company is not telling the truth? Doesn't necessarily mean they're not telling the truth. It could mean whatever her name is really, really unlucky, right? Because it only happened that one time. It only happened that one time. Yep. You bet. Yep.
Why is the threshold 5%?
That's sometimes it's 10%, sometimes it's 5%, but that's where statisticians have decided that we'll kind of understand that a little bit in the second semester. Even though we know that 6% is unlikely, it still happens 6 out of 100 times. Sometimes it's 1%. Okay. All right, everybody else okay? Good? Beautiful? Beautiful. Okay, not necessarily. Our simulation says it's very, very, very unlikely. In fact, it was 0% chance to have to buy 23 or boxes more likely to appear, but the evidence suggests that the company statement's incorrect. It's still possible, however, that NASCAR fan was just flat unlucky, right? They may do it again, and it may only take them 6 boxes. Okay. On the AP Stats exam, you may be asked to describe how to perform a simulation using rows of random digits. If so, provide clear enough description in your process for the reader to get the same results only from your written explanation, not what you're thinking. Like, this makes sense to me. Make sure it makes sense as you read it. Remember that every label needs to be the same length. So if you need 2 digits, we got to use 0, 1, 0, 2, 0, 3. Very seldom are they going to go that high. Okay, beautiful. I hope you got enough to answer these questions. Talk to me.
On this 5.1, are we not use two mapping tests for it whatsoever? Like, what
Not 5.1. The only thing that would show up is, do you think this is likely to happen or not? Fair? On the AP exam, it could say design a simulation. I don't ask that.
So we just think logically, or do we just...
What do you mean logically? I don't want to answer the wrong question.
You said, do you think this is likely, equally likely or not? Like, do you think it's likely or not? Or do you think...
They'll give you the dot plot. They'll give you the dot plot. And then from that, you should be able to know if it's likely or unlikely. Is that fair? Yeah. Great question. Great question. Incidentally, at the end of the semester, this is a 325 secret. If you have one or a couple Z's, I do some things for you guys to fix those at the end of the semester. But don't let it be a whole lot more than 2. Fair? I know sometimes things happen, and I get it, and it's okay. It's a 325 secret. I don't want you to have to take a final because of one bad day or one uh-oh. And I don't want you to have to do it for 2 uh-ohs because we take a lot of freaking homeworks. So at the end of the semester, we can do something to maybe fix a couple of them. 3 is going to be iffy. That's kind of my threshold. It's like that 5%. I didn't say that. They cannot do that. That's illegal. That breaks the rules. Okay. Beautiful. Fingers. Stop. Stop.